Hi, welcome to part 3 of Ultimate Strength Design of Beams. In this video, I prepared 3 sample problems that analyzes the strength capacity of our reinforced concrete section. Ultimate Strength Design of Beams. This video is analysis of SRRB, strength capacity by sample problems. So for this video, we will be solving problems that is analysis of SRRB, applying our knowledge on the previous videos, which are part 1 and part 2 of USD of beams. So for sample problem number 1, we are given determine the strength or the design strength Vm sub n as per NSCP 2015 of the beam section shown. Use Fc prime equal to 27 and Fy equal to 420. This is your section. The effective depth is given to be 600. The base is 375 and it's reinforced by 428 mm bars. Here, even though you are seeing 3 steel bars, that's just for presentation purposes. Pero we are particular that the reinforcement are apat na 28 mm bars. So how can we solve analysis under USD of singly reinforced rectangular beam? The solution that we would follow would be 1. Assume it's yielding. When we assume it's yielding, therefore, we need to check later if it's that means Fs is greater than or equal to Fy. We state and equate that compression is equal to tension in solving for your alpha. The working equation would be this one. Specifying that this is yielding, bakit? Because we're using F sub y. We're using F sub y since we assume that on this step, Fs is greater than or equal to Fy. And as per the code, if Fs is greater than or equal to Fy, we can compute for tension using the yield strength of your steel. Next, after solving for alpha, we need to see if it's acceptable or not. To check whether it's acceptable or not, we need to verify if really Fs is greater than Fy. How can we do that? We can do that by using this equation derived from our previous discussions or previous videos. That would be 600 times D minus C over C. In case that Fs is not greater than Fy, therefore, we need to recalculate for the value of alpha. How can we recalculate the value of alpha? It's still compression equal to tension, but this time, instead of using Fy, we use Fs. When this happens, whether it's yielding or non-yielding, after accepting alpha, we now then determine the type of failure to know your strength reduction, which is phi. Strength reduction can be denoted or taken from conditions of failure, whether it's tension-controlled, compression-controlled, or transition-controlled failure. After knowing your phi and having the value of alpha, we can then solve for your design strength. What's the design strength? The design strength in terms of compression would be phi 0.85 Fc prime, alpha multiplied by B multiplied by the lever arm, which is D minus alpha over 2. Since we can also solve your design strength in terms of tension, we can say that if it's yielding, meaning Fs is greater than Fy, we can use this equation, phi ASFy multiplied by the lever arm. Or, if it's non-yielding, we need to use phi ASFs multiplied by the lever arm. Again, AS is the area of your steel reinforcement. In here, we're using 28 millimeter bars, and there are 4 bars to be used. To continue with our solution, we know that this would be the transform section, denoting that effective depth is 600 from the problem, and if the number of bars is 28. This would be our stress block, and then this is my strain diagram. This is just for illustration. So whether or not you draw this, that's fine. But for my discussion, for better illustration, I prefer to show this to you. So you will not forget what is the lever arm, why d minus alpha over 2 is used for the distance between your force, compression, and tension, and how can we say we use ASFY or ASFS. In here, the strain diagram denotes that the concrete crashes at 0.003 and we are not yet sure what the value of the steel strain, E sub T. For step number 1, we solve for alpha from compression equal to tension, assuming that the steel yields first. Since we're assuming, we'll just say that Fs is greater than or equal to F sub y. This is the working equation. Compression from the figure is 0.85 Fc prime alpha b equated to ASFY. Next, we can rearrange the equation solving for alpha equal to ASFY over 0.85 Fc prime multiplied by b. Everything is given. AS is from the section. Fy is the yield strength of your steel. 0.85 is a constant. Fc prime is also given, and the base is, or the width is 375. Computing for alpha, inserting all the values, it would result to 120.199. And we need to store that value because if this is accepted, we will be using the exact value in computing for your design strength. Remember that your area of steel is taken as 4 and then individual area pi over 4 multiplied by 28 squared. Fy is from the problem, which is 420. Fc prime is 27. Now, having the value of alpha, what we need to do next is see if our assumption in step number 1 is correct. How can we do that? We need to go in checking if Fs is greater than Fy. What would be the working equation? The working equation is given as 600 times d minus c over c. Remembering that c could be presented in this form, alpha equal to c multiplied by beta 1. But before we compute for f sub s, we need to determine our beta 1 because here c is to be used. Since we have c equal to alpha over beta 1 and we already computed for alpha, we need to verify what the value of beta 1 is. If we remember our discussions, since your Fc prime is equal to 27, that is larger than 17 but less than 28, automatically your beta 1 is 0.85. How? We always remember our relationship. This would be 0.85. This would be 0.65. Let's first discuss this one. If it's 0.85, Fc prime, and then this is beta 1. Here, I'm just showing you for better understanding. If my Fc prime is ranging from 17 but less than 28 or equal to these two values, it's 0.85. That's why ito yung ginamit natin. How about for other values? For other values, as we proceed with the next or the future sample problems, you would see how it is different. Now, the working equation would be here, denoting again that C is equal to alpha over beta 1. Since we already have the value of alpha and we have the value of beta 1, we can solve for Fs. Please use the exact value computed for alpha and computed for beta 1 to arrive with this answer, which is 1,945.76. You can pause the video if you want to double check if Fs really is 1,945.76. But always do not forget that alpha should be stored value and the effective depth is given from the problem equal to 600. Since your Fs is greater than Fy, the assumption in step number 1 is correct. It is true that the steel is yielding and therefore Fs is greater than Fy. The next step after accepting alpha is determining the type of failure. Knowing the type of failure would illustrate how your reduction factor is or what is the reduction factor to be used. If we will remember on slide 145, which is conditions of failure, we relate your E sub S or E sub T to your 0.005 or to your ETY. But before doing that, let us solve first for E sub S. The equation would be 0.003 D minus C over C. This is the equation. Please remember that this is only for E sub S. And when you're computing for the exact value, you need to use the stored value for alpha, which is 120.199 something. And then beta 1 is 0.85. Please pause the video if needed and see what would be your value for E sub S. Assuming that you have computed E sub S, this would be your value, 0.00973. This is to be compared either to determine tension control, compression control, or transition failure. Here, we can just say that since E sub C is greater than 0.005, it is tension controlled failure. The reduction factor is 0.9. In case it is not clear to you, you can go back to page 145 of the lecture. Or, for checking purposes only, this is page 145. Since your ES has been proven to be greater than 0.005, ES computed is 0.009 something, therefore, it would be under tension control. The reduction factor or the strength reduction factor in particular to be used is 0.9. We have alpha, we have the reduction factor. Therefore, we can now proceed with step number 4, solving for your design strength. Let's use first the equation for compression, which is phi 0.85 Fc prime alpha B multiplied by the lever R. The working equation would be like this. Inserting all the values of Fc prime, alpha, base equal to 375, effective depth equal to 600, and alpha equal to 120.199. In here, please ensure that you are using the exact values. Since I cannot reflect the exact values because it's continuous, so nilagay ko na lang na 120.199. But you can pause the video and then compute for phi m or phi mn, which is the design strength. The resulting value would be 502.66 kilonewton meter. I hope that you were able to get that same value. If not, please verify or check if you are using the exact values for alpha. If not, recalculate. Make sure that you are following the instructions correctly to arrive with the same answer. As I've mentioned a while ago, you can also compute your design strength in terms of tension. How do we do that? We can either choose ASFY or ASFS for tension, but we need to make sure or to apply the condition since we have proven that Fs is greater than Fy. That means it is yielding. If it's yielding, we will use that working equation. Since Fy is greater than Fs is greater than Fy, we will use this value. The working equation would be 0.94 times pi over 4, 28 squared, times your Fy from the problem is 420, effective depth 600 minus the stored value of alpha. For presentation only, I reflected 120.199, but please make sure you're using the stored value. Computing for Pm or for the design strength, it should result to 502.66 kilonewton meter. Therefore, we are sure whether you're using compression or tension forces, you would result or you would yield the same value for the design strength. In this problem, the design strength, which is phi m sub n, is equal to 502.66 kilonewton meter. I hope that's understandable to you. If there are any questions, you can go back to the previous videos, or you can go back to the discussion from step 1 up to step 4 to yield this value, 502.66 kilonewton meter. To apply more our knowledge and understanding for the analysis of SRRB, let's proceed with the next sample problem. In here, we are still required to compute the design strength of a beam with FC prime 32 megapascal, FY 420, and use NSCP 2015 provisions. The beam has a width of 250 and an effective depth of 380 millimeters. The illustration or the figure would be like this. This is the base, 250, the effective depth, 380, and here it is reinforced with 4 16mm bars. We want to know the capacity, or we want to know the design strength of this section. How can we do that? We'll just apply the same procedure. Assuming that it's yielding, we can compute for alpha from C equal to T. But because we assume it's yielding, we need to use F sub Y. F sub alpha would be accepted if Fs is really greater than Fy. So we need to verify. Fs, to verify, Fs is equal to 600 times D minus C over C. In cases wherein Fs is not actually greater than Fy, what we need to do is recalculate alpha, because alpha from this equation should not be used, because if Fs is less than Fy, it is a non-yielding condition. To do that, use this equation, 0.85 Fc prime C alpha multiplied by B equal to As Fs. After accepting the value of alpha and determining whether it's yielding or non-yielding, we can then proceed in calculating your phi, or strength reduction factor. Strength reduction factor, from time to time, please recall that it's taken after determining whether it's condition, what is the condition of failure, whether it's transition, compression controlled, or tension controlled. Lastly, after having alpha and your phi, you can proceed with computing the design strength. Design strength can be computed in terms of compression or tension. For compression, this is the working equation. 0.85 phi Fc prime alpha B multiplied by the lever arm. For tension, please specify if it's yielding or non-yielding. If it's yielding, use ASFY for tension. If it's non-yielding, use ASFS for tension. So much for the recap of your solution. Let's proceed with the actual computation. For illustration, I have shown you, or I am projecting the transform section, the stress block, and the strain diagram of your figure in sample problem number 2. This is with an effective depth 380 millimeters and reinforcement apat na 16 mm bars. Again, please do not mind that there are only 3 reinforcements here. This is just for presentation. Solving for alpha from C equal to T, assuming it's yielding, therefore, we need to verify later if Fs is greater than Fy. This would be your working equation. It's just similar to what we did in sample problem number 1. Your alpha would be like this. Here, As becomes 4 times pi over 4. Please compute with me so you can verify if your answer later would be the same with my computed alpha. 16 squared. Fy here is given to be, let's just go back. Nakalimutan ko. I'm sorry. So I think Fy here is $420 and Fc prime is 32. Okay. So 420 over 0.85 over 0.85, Fc prime is given to be 32 and the base is given to be to 50. Pause the video if you need to and compute for alpha. Using this equation, medyo magulo to. Burahin ko na lang. So, rewrite ko na lang yung 420. Okay, we can solve for alpha. Alpha would be equal to 49.674. I hope that you get the same answer. If you got the same answer, we can proceed with the next step. If not, pause the video and please calculate or try to solve for alpha, and I hope that you will result to 49.674. Step number 2 is checking if our assumption in step number 1 is correct. We need to prove, or we need to see if Fs is really greater than Fy. If this is the case, the working equation for F sub S is 600 times D minus C over C. Remembering that alpha is equal to C multiplied by beta 1. So we can solve for C in terms of alpha and beta 1. But let's first go in determining the value of beta 1. In here, your Fc prime is already 32. It's greater than 28 but less than 55. So what would be the value of your beta 1? Pause the video to remember, or if you want to try to remember the working equation in beta 1. The working equation would be 0.85 minus our formula to get for beta 1 is 0.05 times Fc prime minus 28 over 7. In cases wherein we're using 2001, this will change and would be use 30. But because we're using 2015, we will use minus 28. Just for future reference. The value of your beta 1 would be, pause the video if you want and solve for beta 1. I hope that you will get this answer, 0.82142, which would be stored value. Why? Because when we use this in computing for our design strength, we need to use exact values only. Because we are dealing with kilonewton meter for the moment, and other values are in Newton or in millimeter squared, meaning that those are with a factor of 1 million. So a little difference or rounding off of values would result to discrepancy on the final answer. In reinforced concrete design, always round off your answer to, always do the rounding off with your final answers. With our value alpha, 49.674, and beta 1 equal to 0.82142, we can then compute for F sub S. What is F sub S? F sub S is 600 times D, expressing C in terms of alpha, equal to alpha over beta 1 over alpha over beta 1. Please, you can pause the video and try to compute for F sub S. Use exact values only. Computing for Fs would yield 3,170.29. If this is not your answer, pause the video and try to recalculate F sub S. I have already checked the final answer and this is already correct. So, sana lumalabas yung 3,170.29 sa inyo. Since Fs is greater than F sub Y, assumption in step 1 is correct. We can accept alpha, and so we can go to step number 3. Dito sa step 1 and step 2, it is done because you want to make sure if your equation here is correct or not. Kapag dahil ginamit mo yung Fy, dapat sigurado ka na yielding siya. Malalaman mo lang na yielding siya kapag Fs is greater than Fy. Next, determine the type of failure. To determine the type of failure, we go back or recall that ES should be compared to 0.005 or ETY. 0.003 times D minus C over C would result to what value? You can express C in terms of alpha. This means that I can change this as alpha over beta 1. This also as alpha over beta 1. Please use exact values only and pause the video to see if you can compute for the correct value of ES. Considering that you have paused the video and computed for ES, this is the value 0.0158. This value is again greater than 0.005. As we've done on a previous problem, we went back to page 145, which is the conditions of failure. But here, I will no longer show page 145. By this time, I hope that you already have a grasp why we're using phi equal to 0.9. Because since or ES is greater than 0.005, it will fall under the tension-controlled failure. And under tension-controlled failure, the strength reduction factor is 0.9. We have alpha. We also have your reduction factor phi. Now, we can proceed with the next step, solving for the design strength. Let's solve the design strength in terms of compression. If you want, you can pause the video and see and check what's your understanding by writing the equation on your own. If you have paused the video and wrote the equation for PMN in terms of compression, please check if this is the one you have. 0.85 times phi Fc prime alpha b multiplied by the lever arm. Using all the values from the geometry of the section and the exact values of alpha, this would be your working equation. Again, only for presentation, I reflected alpha to be 49.674. But please do not forget that alpha is, the alpha value to be used should be exact. You can pause the video for a while computing for PM and check if you got the correct answer. If you have paused the video and computed for the design strength, it should be equal to 107.97. For illustration, I would show you that we can actually compute also our design strength in terms of tension, provided that we use the correct equation. ASFY for tension if it's yielding, ASFS for non-yielding. Please check or please try if you can solve for Pm using the correct equation. In here, you should have the idea that the correct equation to use is, since Fs is greater than Fy, we will use the yielding equation. This is the value 0.9 times 4 times pi over 4 times 16 squared times 420 multiplied by the lever arm, that is equal to 380 minus alpha over 2. For alpha, use the stored value. We would see that it's just equal to 107.97. So the purpose of me showing you that you can compute for the design strength, whether for compression or tension, is would allow you to stop your solution with this one already. Pwede naman yun. Dito, already the final answer would be 107.97. But it's not harmful to try this one. Therefore, the design strength would be 107.97. So far, we have solved 2 sample problems wherein both are yielding. Let's try a sample problem which is formula-based, meaning it would help if you're familiar with the working equation. If this sample problem is unclear or if you have questions, you can always go back to the previous lectures and you can go back to step 1 of sample problem 2. If not, let's continue this discussion. The next is sample problem 3. As I told you, we will use a formula only. A reinforced rectangular beam, base 400 and effective depth 720 is reinforced for tension only at 6 or with 6 25 mm bars. Fc prime to be used is 21, Fy is 400 megapascal. Determine the coefficient of resistance, R, and the reinforcement index, omega or W. Whatever fits you, okay lang. Dito, ang nakita natin is it helps if you are familiar with the equation. Remembering, your R is actually equal to rho Fy multiplied by 1 minus 0.59 rho Fy over Fc prime. In this equation, Fy is given, Fc is given, Fy is given. But rho, if we can remember, is just your steal ratio. It's equal to As over BD. If we continue our equation, your working values are as follows. Pause the video and please try to compute for R, which is your flexure resistance factor. That is 6 times pi over 4, 25 squared over 400 times 720 times the Fy, which is 400, multiplied by the quantity 1 minus 0.59 times rho Fy over 21. The value for R would be 3.62. Again, this is just formula-based. After solving for R, we need to compute for the reinforcement index. But reinforcement index is just rho Fy over Fc prime. Here, if we take out 0.59 and then we isolate this one or this term, we already have computed for the reinforcement index, which would be 0.195. Before proceeding, please check if you can get 0.195. So far, there are 3 problems that we have solved. Problems 1 and 2, and this 3 is application of the direct formula. On the next video, we will be solving 3 more problems. One of the problem is yielding Fs less than Fy. So we would now see, or we would now know paano nangyayari kapag ang Fs mo is less than your Fy. I hope that I can see you on my next video, and thank you for watching. Bye-bye.